Yeah. So yeah, my name is Matthias Jung. I'm working here in Kaiserslautern at the Fraunhofer Institute IESE, and today I will present in half an hour some details about our DRAMSys simulator. And since we are here on the MBMV workshop, my focus today won't be too much on results and optimizations. I think I will mostly focus here on the topics of modeling, the functional models, also the DRAM modeling language that we have developed. So that will be mainly the focus of the talk, but I will also show a little bit things about non-functional simulations and also how we can do analysis with our trace analyzer tool. Okay, so let's see. Yeah, so DRAMSys in a nutshell, it's a design space exploration framework for modern DRAM-based memory systems. So that means, for example, which DRAM configuration should I use for my system? Yeah, so what our customers currently asking for is, okay, when should I go for DDR5? What would be my advantage? What is different in the new standards like LPDDR5 in automotive, for example? So these are the questions that we try to answer with the tool. So how can I configure my memory controller? What are the best strategies with respect to refresh? I think we have seen that already from Luca's talk in the morning. And of course, also, what is the system level behavior? So what is the influence of my memory system on my system level application behavior? So what DRAMSys offers is high speed, flexible, and very accurate models of the DRAM subsystem. And you can use it for fast and accurate design space exploration and for early identification of bottlenecks. And of course, since it's based on SystemC, you can connect it to everything what is also SystemC, and also, for example, to Gem5 for the research path. Yeah, so DRAMSys is open source. We have open sourced all the established models already. There is a but, so there are commercial licenses for DDR5 and LPDDR5. So always the newest memory technology is not available on GitHub, but we have also academic licenses, so for universities, such that they can also do some analysis here. But after some time, if the DRAMs are established and also out there in the market and are used, then of course we will also open source these old models. And we are really happy about one of our key customers here, which is Rambus. And this makes us really proud that they use now DRAMSys also internally for their analysis. Yeah, I said it already. Let's first look on the functional models that we support in DRAMSys. And before we do that, I want to give a quick overview on the different kinds of DRAM simulators that we have. So we have cycle accurate models. These are the ones that we want to look on today, and we have non-cycle accurate models. So we have, for example, pure functional models with fixed latency. So one DRAM access is 40 nanoseconds, and you can see already this is really inaccurate, but it is of course really fast. And then we have cycle approximate models, like analytical models. We have seen that already today, statistical models, and even neural networks. So that's also something that we tried. But today we want to look on the left side of the diagram. So we have, of course, this discrete event simulations. RTL models is the classic example. We have also just C++ based models that have their own simulation kernels. There are a lot of DRAM simulators out there. And then there's our simulator, which is also cycle accurate, but it's based on SystemC transaction level modeling, and therefore it's much faster compared to RTL. I will show you that in a minute. Yeah, as I said, DRAMSys is based on SystemC TLM-2, and is completely compliant with the approximately timed coding style, because we need out-of-order communication, and we can model a variety of standards, and this is basically the architecture. And you can see we are fully TLM compliant, but here we have a custom protocol developed, which allows us the higher amount of accuracy. So let's have a look on this custom protocol. Simulation speed can usually be increased by reducing the number of events. And in an RTL simulation, of course, the clock signal has the highest event generation rate. And the question for DRAMs is, do we really need to simulate each and every clock cycle to generate cycle accurate results? And the answer is obviously no. So in RTL, this would be basically the simulation of a DRAM bus sequence of an activate and a read command. And you see there the timing dependency. So from this activate command that is issued to the issuing of the read command, you have to wait TRCD. Keep that in mind, that will be important later on as well. And if you move to TLM, we just get rid of the clock and just look on the events, basically when is the activate issued, and then we know this timing dependencies, and then we know when the read has to be issued, and we just simulate these events. So we directly jump from here to here, and this will give us a huge speed up. Yeah? So we can skip idle clock cycles and even idle time in the memory. This is not simulated in DRAMSys. And for that reason, basically, we have a large simulation speed. And also no loss of accuracy, because we have a clever coding technique. You will see that also in a minute. And therefore, we can maintain the accuracy. Yeah, that's the basic concept of DRAMSys. And yeah, here I showed an example basically for the simulation speed. So this is RTL as a baseline, and here you see the memory access density. So that means here we use the DRAM extensively, so high memory utilization, and here we don't talk to the DRAM at all. And there you can see basically these loop-based simulators also simulate each and every clock cycle, but they don't have the overhead of a SystemC kernel, for example. So they have their own custom kernel. And here you can see then the DRAMSys TLM, which offers you, especially when you don't talk to the memory system, a high simulation speed. But of course, if you use it more extensively, the speed up converges to the clock-based simulators, because we have the same amount of events. So that's basically DRAMSys and the advantages of it, and it has the same accuracy as RTL models. So one of the problems is basically that almost every year we get a new memory standard. And for us, is it a huge effort every time when a new standard comes out, we have to build a new model. And therefore we invented this DRAMMl language, and I will introduce this now. So when you look on a JEDEC standard, it's really complex. So Lucas mentioned it already this morning. It has almost 500 pages nowadays, full with timing diagrams and tables and timing dependencies and requirements and so on and so forth. And one of the problems is that these descriptions are human readable, but not really formal and not even correct. So I don't want to go so much into detail here, but if you read already the sentence here, this simplified state diagram is intended to provide an overview of the possible state transitions and the commands to control them, in particular situations involving more than one bank. The enabling or disabling of one die termination and some other events are not captured in full detail. So when you look at the state machine, you see already, okay, it supports only one bank. So DRAMs have nowadays 8, 16, 32 banks. So you cannot show the bank parallelism in this. There are states like activating, pre-charging, and so on and so forth. They do not really exist. These are transitions, but not really states. So in DRAMs, we have just only 5 states, basically. Self-refresh, idle, power down, and a power down pre-charge, power down active, and bank active. And then we have some double states, which is also interesting. And we have also some inconsistencies related to the transitions of these states, basically. So we need a comprehensive mathematical model of DRAM states and commands and also of the timing. And this is where this DRAMMl kicks in. So as I said, a new standard requires always a serious amount of handcrafting, new models for simulation and verification. We have to adapt our models and also the hardware IP every time a new standard comes out. And in the ideal case, we would have a formal language which has the power to basically compress all these JEDEC pages in a human and machine readable format. So that's basically what we have. That's the first thing. And then secondly, it should also correctly describe the DRAM protocols, also in an intuitive and comprehensive and extensible manner. And the holy grail basically is then from this language to generate our simulation models. And this is basically what we do. But I want to show you first a little bit the semantic behind this, because the semantic of this domain-specific language, DRAMMl, is basically Petrinets. So we have a look on how we can model DRAMs with Petrinets. And I don't want to bore you so much, and I have just some simple examples, and I assume everybody here knows what a Petrinet is. So if we look on a single DRAM bank here, we have basically some rows and some columns, and we can always latch basically one of these rows into row buffer here. And compared to the state machine, we model now the states of the DRAM with the places of the Petrinet, and we model the DRAM commands as the transitions. And in the beginning, we're under idle state. And if you want to read and write, or read or write, we have to go into the active state. So we send an activate command to the DRAM, and then basically we get the data from this specific row into our row buffer, and we move the token from the idle state to the active state. And now we can perform read operations, we can perform write operations. And if we are done and we want to read data from another row, we just issue a pre-charge command and we are back in the idle state. And this works also pretty well for two banks. So we activate one bank and we activate the same bank again. Oh, no, this doesn't make any sense. So let's go back. We have to put here an inhibitor arg such that we activate one bank. We are not allowed to activate it again. And now this scales, so we can have 8 banks. And if you look on the same thing on a flat state machine, you can see basically the power of parallelism, again, of Petrinets. And now you also understand why JEDEC people don't want to draw the full diagram. So what we did basically, we created this Petrinet semantics, and we described basically with that the DRAMs in a very comprehensive manner, with clear separation between states and commands. We find our 5 states again that I talked about before. We support now multiple banks, so we can support the bank parallelism in the DRAM. And we have then, of course, also different subnets for banks, refresh, power down, bank groups, and ranks. So now what's about the timing? So you have seen that in DRAM we have these timing dependencies. So when we issue here the activate command, we have to wait TRCD clock cycles until we are allowed to send a read command. And then we have to wait TCCD cycles in order to send the next read command. And then after some time here, the CAS latency, some data is coming to the output of the DRAM device. And this protocol is really complex. So you will see that in 2 slides, and then you believe me that this is a really complex protocol. And even already for DDR3, 90 pages of these 260 pages of the JEDEC standard, they are just showing timing diagrams and explain these timings. And what we have introduced basically is then a special timing arc here, which just consists of a place, a timed inhibitor, and a reset arc. And with this custom arc, we can basically describe these kind of timing dependencies. And as I said, for activate and read, this would be, for example, TRCD, and then we would draw between an activate transition and a read transition an arc with the TRCD on top. So further timing dependencies like refresh, command bus, and TFAF are explained in the paper that we published on the MEMSIS conference on this. And if we add now timing to our picture, it will look like this. And this is an artificial DRAM with just 2 banks. So if we now go to a DRAM, for example, with 8 banks, it's already really hard to render this image. So one solution is, of course, to bring hierarchy into that. And I will show you how we did that. So we have now these time Petrinets to allow us to model DRAMs in a formal way. As I said, graphical handling is just possible if you would use hierarchy, but we want to go to something that is, code basically. And for that reason, we came up with the DRAMml idea. This is a domain-specific language to describe DRAM's behavior with Petrinet semantics. So what we can do is we can compress such a JEDEC standard basically in just one single page, describing all these timing dependencies in a very compact fashion. And this DSL is now the basis for correct by construction code generation of SystemC code that we will use in DRAMSys. And with that move, we have solved the problem when a new standard comes out. So for example, when DDR5 was published, it took us just 2 weeks to implement the complete model. And most of the code, or the most important code of this model, we could generate out of this domain-specific language. Yeah, so here you can see now, just as an example, a complete description of this DRAM modeling language. I don't want to go into detail. I just want to make you believe basically that it fits on a single page. So if you look again, there is this activate to read, and there you can see again our TRCD timing dependencies. And the first value basically is within a bank, and the second value is among the banks. And this is basically how we solve this problem of hierarchy. So you see this file consists basically of a DRAM description. A DRAM consists of a device, and the device consists then of a specific number of banks that could be also configurable. So you see that the hierarchy is basically described in this DSL. Okay, so let's look now on these non-functional properties like power, thermal, and retention errors, for example. So what we built up is a holistic simulation scenario here, where we used, for example, Gem5 together with DRAMSys, so Gem5 for modeling multi-core systems. And we have also another tool, which is called DRAM Power, which can basically calculate the power consumption and energy from these stimuli that are basically coming into DRAMSys. And from these power calculations, we fill or feed basically a thermal model. In this case, we have a focus, of course, on 3D stacked memories, because there we have some thermal problems. And then also these thermal results, temperature simulation goes back, and then we close the loop and have a full system simulation. And for example, then we can change the refresh strategy according to the temperature, or for example, the voltage and frequency scaling of the cores to cool down the system. So I show you here also a simulation of that we did already some years ago. So this is a 3D MP SoC with 4 ARM cores. It is Cortex A9, and then 4 channels stacked by the I/O DRAM. We are running Android OS on Gem5 here, and we also did dynamic voltage and frequency scaling for the cores. and some refresh optimizations as well. And then we have a closed loop simulation, and also we put temperature sensors into the memory. So if I start this now, you can basically see how the cores are computing and then heating up this 3D stacked memory stack. And you can then also observe something really interesting. Namely that we have different temperatures in our stack. And that's something that we exploited basically for refresh optimizations. Of course, the parts of the memory which have a higher temperature, we have to refresh more often. And this was basically one of the research papers that we published in the past. Yeah, so coming now to the last thing. So we talked about non-functional models now. Now let's have a look on the trace analyzer. And let me bring you the window of it here. So I hope you can see it. Try to make it a little bit bigger. So here basically you can observe really what's going on in the DRAM. So I zoom a little bit out. In the top, basically, you see the TLM transactions that come in. So maybe I just search for something, some part in our application where something happens. So basically here. So a specific transaction comes in. And then if it's scheduled by our memory controller, we submit a read command, basically to the memory and execute it, and the data comes out, and then we send out the TLM response, basically. So here you see we have always row hits. So all the DRAM reads go to the same location, to the same row, basically, and we have row hits and a linear or very structured access. And then we switch from one bank to the other bank. So the lines that you see here are the different banks. But in that bank, another row was open before, so we have to issue first a pre-charge command and then an activate command. And the timing that I showed you before basically was then from the beginning of the activate and then here to the beginning of the read. So this was the TRCD, which is just 12 nanoseconds here, for example. So as you saw, basically DRAMSys is not simulating each and every clock cycle, but it's still cycle accurate because it really follows the timing rules of the JEDEC standard. Yeah, so, but we get a speed up because basically we jump from this event to this event, but here it does not make any difference because we have still a lot of events, and there you see basically it's almost approaching the cycle accurate thing, but it's still faster because it still can jump basically from here directly to here. So if we go somewhere else into this application, we see, oh, here's the DRAM is really idle, so nothing really happens. From time to time, a refresh happens. And when we zoom out here, you see that in this scenario, we do not simulate all these clock cycles. We really fast forward from this clock cycle basically to this one. And this is where the huge speed up comes from. So besides understanding what's going on in the DRAM, so if you, for example, see here, we have a very good data bus utilization here, almost 100%. We have just some small bubbles here on the data bus. And if you see here, the bandwidth is not so high, but also the requesting rate is not that high. So this is also the same here. Why we have these bubbles, basically, because our CPU does not request each and every clock cycle something from our memory. So maybe let's find some position in this trace here, in this application, where we have maybe a memory problem. And for that reason, we also have a tool here which is called latency analysis. And here now you can basically see what is the the latency distribution for this application. And then it's of course important that we look on the tail. So why we have here almost 500 nanoseconds latency. So we can basically go there and pick out this transaction and go there and can then understand what is going on. Yeah, so we can really analyze here our application behavior, how are the banks utilized, what is the problem here. So we see here there are a lot of row misses, and then we could think about strategies, maybe how to make this better. Yeah, furthermore, we have some other analysis tools, for example, power. We can, of course, plot the power consumption over time here with our DRAM power tool. We can also check the bandwidth over time. So you see that we have some bandwidth peaks. So this application is not trying to get everything out of the memory. So maybe I just open another one that you can also see this. So this is really an application that tries to get as many requests from the memory, but also you see it's a completely random access. So all the addresses are really random, and then you can see that we always have to make these pre-charges and activates, because every time we will have row misses because the trace has no locality at all. Okay, so I don't want to to bore you now. The last thing that I want to show you basically is this tool. So we have a Python interface, and there you can basically describe some metrics, and all the metrics that are described in Python, and you put a decorator in front of the function name, you can then also calculate automatically here in the tool. And so because it takes too long if we do all of them, so we just get again maybe the average response latency and maybe the bank utilization, something like that. And then it computes in the background, and hopefully it will give us then in a second the results. Okay, so basically you see here now this is the average latency that we have for this specific simulation here. And here we can see that most of the time we have 7 banks active at the same time, and these are important metrics for memory design. Okay, so having that said, I will end now my talk, and I hope that you have also some questions for me now.